All right, next example we have, example 2. We are to determine the flux of the vector field zx1 across the upper hemisphere of the unit sphere. And we want that upper hemisphere oriented with outward pointing normal vectors. So let's first think of the sphere. So here's our hemisphere, I should say. Here's our hemisphere. And we know that on the top half of the sphere, the upper hemisphere, if our normal vectors are to be oriented like that, then this is outward. And no matter where we draw an outward vector on our hemisphere here, notice that all of these vectors have an upward tilt. So outward on the upper hemisphere means upward. Because if you think about it, on the lower half, outward actually means downward. So outward can mean upward or downward depending on which half of the sphere you are on. So just being really clear here, for us, outward will be translated to mean upward. In other words, z component should be positive. All right, so the usual parameterization of a sphere or any portion of a sphere is based upon spherical coordinates. So we'll have coefficients of 1 since it's the unit sphere. So we'll have cosine u sine v, sine u sine v, cosine v. In a previous example, we have seen that the proper order to cross our partials in to obtain an outward pointing normal vector, in other words upwards on the upper hemisphere, is in the order rv cross ru. Doing so produces the vector cosine u sine squared v, sine u sine squared v, sine v, cosine v. And we can check here that this z component is in fact positive because the parameter v only ranges over from this angle here, which is an angle of 0, all the way down, if you think of tilting this continuously, all the way down to this angle here, which is a right angle pi over 2. So let's be real specific here. Let's drop this down and just say we're going to define this for points u comma v between, u between 0 and 2 pi, and v between 0 and pi over 2. So v being between 0 and pi over 2, that's a first quadrant angle. This is positive times positive, which is positive. So what we can do now is calculate our surface integral f dot ds. This will be the double integral over our parameter domain d, and our parameter domain d is right here. That's what constitutes d. So this will be the double integral over d. We will take our vector field, which is z. So we'll take the z component of our surface parameterization. X, so we'll take the x component of our parameterization, which is cosine u sine v. And then we will take 1 and leave it alone since it's a constant. Then we will dot it with our appropriately oriented normal vector. So cosine u sine squared v, sine u sine squared v, and sine v cosine v dA, and dA will ultimately become du dv or dv du, depending upon the order of integration. So I'll continue to write this generically over the domain D, and I will go ahead and do the dot product. So we'll obtain cosine u sine squared v cosine v plus sine u cosine u sine cubed v plus sine v cosine v dA. So that is quite nasty looking. Things that you should always think to do or look to do when you are doing a integral like this, where you've got sines and cosines to different powers, different terms being added together. Hopefully the first thing that goes through your mind is, I should be able to maybe get an identity to pop out of here. Maybe I can collapse some terms, right? Maybe we can find like a sine squared v plus cosine squared v, and then if we can find that, we can get 1. That's wonderful. Definitely do that first. It just so happens here that although we have a sine squared v, there is not a single cosine squared v. So that identity is not going to pop up unless we try to make it pop up, and then even then that's going to cause some issues probably. It's not naturally here, so let's ignore it. But let's think about our domain of integration. We're going to have to do a u integral over 0 to 2 pi and v integrals over 0 to pi over 2. So let's examine each of these separately, and let's first look at the u integrals first. Why would we look at the u integrals first? Well, whenever you integrate a trig function over one full period, or any whole number multiple of a full period, there's a good chance that maybe some of your integrals end up being 0. Why? Well, think about the graph of sine. It's periodic. This area down here is exactly the same as this area up here, but this area is positive, this area is negative. So if this is the u-axis, and we're going to do the integral of sine of u du over 0 to 2 pi, right, this is 2 pi, then this would be 0, because the areas would cancel out. So let's see if that happens. So this first term here, we have a single u term. So in this integral here, for this one term right here, this will be the integral from 0 to 2 pi cosine of u du, which is 0 for the same reason. We've got cosine, right? So this area here and here is positive, and it perfectly cancels out with this equal but opposite area down here, so we get 0 for that integral. And because we get 0 for this one integral, this entire term goes to 0. Doesn't matter what this integral is, because whatever this numeric answer is, it's going to be multiplied by 0. So the whole thing goes to 0. All right? What about this term? Here's our u integral here. If we look at this, 0 to 2 pi sine u cosine u du. What we could do here is let's say we could let w equal sine of u, then dw would equal cosine of u du, and then w of 0 is sine of 0, which is 0, and w of pi over 2 is the sine of pi over 2, which is not pi over 2, excuse me, sine of 2 pi, which is sine of 2 pi, which is 0. So this would turn into the integral from 0 to 0 w dw, which is 0, because these two numbers are the same. We're looking under the graph of w, right? If this is the w-axis, this is the line w. We are starting here, and we are not traveling anywhere. So there's no area, because there is no width of the rectangle. So that's 0, so this entire term is also 0. Now over here, there is no u in this expression, which means that if we just do the integral of du from 0 to 2 pi, we'll get 2 pi. So if we do this, we'll have 2 pi, the integral from 0 to pi over 2, sine of v cosine of v dv, and then we can use a similar substitution that we had here. We will go ahead and let w equal the sine of v, dw will be the cosine of v dv, w of 0 is 0, w of pi over 2 is the sine of pi over 2, which is 1. So this becomes 2 pi integral 0 to 1 w dw, which is 1/2 w squared between 0 and 1, which is pi.